Hello everyone, I am Andrei Anghel, and in this presentation I will highlight the latest advances in a bistatic synthetic aperture radar system designed for space ground sensing. The envisaged system consists of a ground-based stationary bistatic receiver that uses a SAR satellite as transmitter of opportunity. The ground receiver has at least two channels. One channel that receives directly the transmitted pulses from an antenna pointing towards the satellite, called the reference channel, whereas the others receive the reflected signals from an antenna pointing towards the imaged scene. The results obtained in the Spaceborne transmitter stationary receiver bistatic SAR framework rely on two ESA-funded projects, COBIS and Tomosar-1B, and include various hardware and software developments. Aspects like ground receiver architecture design, transmitter-receiver synchronization, repeat-pass single-pass bistatic SAR interferometry were performed within the COBIS project. Currently, in the Tomosar project, we are working on a miniaturization of the ground receiver in the context of single-pass bistatic SAR tomography. Additionally, two research directions based on bistatic data are under development. Multi-aperture focusing used to increase cross-range resolution of bistatic TOPS data and bistatic SAR polarimetry. In the case of single-pass bistatic SAR tomography, the elevation aperture is formed at the receiver level using a vertically placed antenna array. It can be shown that using the co-array concept, we can use a simple non-uniform array with three antennas to obtain similar estimation performances with a uniform linear array with 7 antennas if there are no more than 2 targets in the same range azimuth beam. Moreover, such a configuration achieves better estimation accuracies than a uniform linear array with 3 antennas. Ongoing work involves experimental validation of single-pass tomography using the non-uniform linear array. In the considered bistatic configuration, if the satellite operates in a multi-SWAT mode, the same area on the ground can be illuminated from several sub-SWATs. Hence, in one acquisition, we receive pulses from multiple bursts with some gaps in between. Multi-burst data can be used to enhance the cross-range resolution. The bistatic azimuth signal after range compression consists in complex exponentials with slowly varying frequency. The azimuth antenna pattern that modulates the reflected signals can be compensated using the reference channel signal. A direct integration of multi-burst data with gaps would lead to focusing artifacts. Therefore, we use an autoregressive model or a compressive sensing-based method to fill the gaps between the apertures before the azimuth focusing. This approach leads to an enhanced cross-range resolution. The potential for new information that can be extracted from bistatic polarimetric data is currently unexplored by Earth observation missions. One of the main reasons is that today there is no truly bistatic Spaceborne SAR mission to provide this data, and Spaceborne transmitter station receiver bistatic SAR systems can be employed for the exploration of the bistatic scattering processes. A preliminary assessment of bistatic SAR polarimetry was performed with the COBIS platform by using antennas with orthogonal polarizations on different channels. The polarimetric images are acquired over an array of Bucharest city, Romania, with the ground receiver placed on top of the university building. VV and HV data were analyzed using a dual-pole H-alpha decomposition. Most of the scatterers are placed at low entropy values, and the first classification can be made according to the average scattering angle. Further investigations will be made to understand the changes of the dual-pole H-alpha zones in bistatic geometry. To conclude, several developments have been made around the ground-based bistatic platforms: repeat-pass single-pass interferometry, single-pass tomography, cross-range resolution enhancement, and bistatic polarimetry. In the future, we aim to use the bistatic receiver as testbed in risk retirement activities for the Harmony mission, to perform various experiments that exploit bistatic diversity for polarimetric target characterization, and to apply machine learning approaches to extract relevant information from monostatic and bistatic data.